I'm Dr. Chris Creighton, and this is a supplement to one-to-one and invertible functions. So the first example is determining if a function is one-to-one and inverting it is f of x is equal to x squared plus 3. So let's try to check this via the functional one. Now, the quick way of doing it is if we were to graph it, this function looks like this, where this value down here is at -3. That's a very quick sketch, I'll be honest with you. But initially, you can see that this thing is very much not one-to-one. So if I pick whatever value that is, we see 1, 2. That will correspond to two different things. This is not 1-to-1. Functionally, checking that, f of x is equal to f of y. That would correspond to x squared minus 3 is equal to y squared minus 3. So then x squared is equal to y squared. And then here's the tricky bit. This is what messes a lot of people up. If you take the square root of both sides, you get both the plus and minus root. This is your big issue. You have two solutions. So this leads us back to not being one-to-one. But what if, for instance, we could exclude one of them? All right? So like for instance, if we were to just make the declaration, say restrict x to being just completely positive. So if we make a domain restriction now, that would eliminate that negative root. X cannot be negative, so we can't get that -1. So in this case here, we sort of just go like, okay, we don't care about that side. We're just going to focus over here where this thing is one-to-one. We took off that issue on the negative axis. So if we were to restrict it, then it is 1-to-1. So very often with problems like this one, if you don't see a restriction, if you quickly check it and you see that it's not 1-to-1, you can't invert it. But if you see it with the restriction, then it is 1-to-1 and you can invert it. So in this case here, inverting it, we see that y is equal to x squared minus 3. So the first thing to do is replace f of x is equal to y. Swapping, we get x is equal to y squared minus 3. So that's the next step. We swap the two. Now we need to solve for y. So then we get y squared is equal to an x plus 3. And then we take the square root. Y is equal to plus or minus square root of an x plus 3. So in this case here, knowing that we have this restriction of x being positive, we can actually not take that negative root. Because we swap the x's and y, so this thing, when you swap, turns into y is greater than 0. So we actually don't have that negative root. So in this case here, we have f inverse of x, which is just equal to this y value, is equal to the square root of an x plus 3. So in fact, things that are squared are counteracted or inverted by square roots if restricted down to a one-to-one space. Just like if you have a square root and you square it, that undoes the root. So squaring things undoes square roots. Taking square roots with the domain restriction undoes things that are squared. So now this is a bit trickier. This is pretty much the trickiest one that we'll see. So getting through this, you feel good about it, then you'll be doing fine. So in this case here, we have f of x is equal to x plus 1 divided by x plus 2. So we need to determine if this thing is first 1-to-1, and if it is, then invert it. So in this case here, I'm going to check this functionally, because checking this graphically is quite tedious. So f of x is equal to f of y. So then we get x plus 1 divided by x minus 2 is equal to y plus 1 divided by y minus 2. And then you go like, there are fractions of fractions. So what I'm going to do is do the little cross multiplying. So in this case here, we get x plus 1 times y minus 2. This is equal to an x minus 2 times a y plus 1. So I multiplied this up to here and that up to here. So really I multiplied both sides by a common denominator of x minus 2 times x or y minus 2. Now you're like, okay, great. Now I have these terrible polynomials. I'm just going to multiply them out, trust the process. So in this case here, we get xy plus y minus 2x minus 2. That is equal to xy minus 2y plus x minus 2. And then you start to go, wait, both sides have a negative 2, both sides have an x. So this turns into y minus 2x is equal to minus 2y plus x. Which is great, because like those two go away, those two go away. So now if I add 2y to this side to give myself 3y, and then if I add the 2x to the other side, I'll give us 3x. So then y is equal to x. So this thing is 1, 2, 1. And I'll just be honest with you. I'm doing this to demonstrate how this goes. I would be happy with if you said this is a rational function with linear terms. Well, we'll say numerator and denominator. That implies that this thing is 1-to-1. All right. So things of this form, x plus 1 divided by x minus 2, these things are always 1-to-1. So you don't necessarily need to go through this entire process, but it's good to at least see it. So you can just say, hey, this thing is 1-to-1. Now if I made that like an x squared on top, then no. Now we can invert it. And you can probably guess based upon the algebra we did over there, a little bit tedious. So again, the first step is writing y is equal to x plus 1 divided by x minus 2. Now swapping all the x's and y's, we get x is equal to y plus 1 divided by y minus 2. And again, hate fraction, so I'm going to multiply both sides by the y minus 2. So I get x times y minus 2 is equal to y plus 1. Multiplying xy minus 2x is equal to y plus 1. And again, solving for y means we have to group all the y's on one side. So I get xy minus y is equal to 2x plus 1. I moved everything with a y to the left side and everything without a y to the right side. Factoring y, x minus 1, is equal to 2x plus 1. So y, which is equal to f inverse of x, is equal to 2x plus 1 divided by x minus, not minus 2, minus 1. So now we got our inverse function.